4、3、2、Q.
My dear professor, our research is Dang Beratu遇上史坦纳 synergy in Platonic polyhedron.
This is our introduction. First, in triangle ABC, we want to find points S, such that the sum of the distance of segment SA, segment SB, and segment SC is shortest, so we call point S is Fermat point. And second, in a convex polygon with more than 3 vertices, then we added some points, etc., such that the sum of the distance of vertices to S1, S2, then we added its shortest, so we call points S1, S2 is standard points, and the dark blue path is standard trees. This is our purpose. First, find the standard points in a regular polygon. Second, compare the shortest path from mathematical model and the bubble salt film from a wire model. Third, find the standard point and the standard tree in Platonic polyhedron. This is our research equipment.
Material and method. In our study, we start from the standard tree of convex n-gon, and then generalize the standard tree of Platonic polyhedron. Now we are going to introduce planar graph. First, the Fermat point of triangle. There are two cases. First case is the largest angle is less than 120 degrees, and the second one is the largest angle is not less than 120 degrees. And in our study, we only use the first one. And the method is we choose segment AB and segment AC to make equilateral triangles. Then we connect segment QCA and segment BS, which intersect at point P. So it is the Fermat point of triangle. Then the standard point of square. We choose the parallel side to make equilateral triangles and circles. Then connect segment EF. So S1 and S2 are the standard point of square. Then in the other hand, we choose point G as the gravity of square, and we consider the Fermat point of triangle GAD and triangle GBC, and which are S1 and S2. So they are the standard point of square. And the standard point of rectangle, we choose the shorter side to make equilateral triangles. So S1 and S2 are the standard point of rectangle.
Next, we're talking about Platonic polyhedron. This is our topic. Next, we'll introduce the standard tree of tetrahedron. There are 4 faces, 4 vertices, and 6 edges in tetrahedron. By former experience, we use the same way in square. We consider the triangle GAB and triangle GCD. We find the standard point is S1, S2, and the right path is standard tree of tetrahedron. Next, we'll check the bubble salt from our model. We made a copper wire model with each side is 10 cm and another one is 20 cm. We put it into bubble water, pour it upwards vertically and 45 degrees repeatedly. There are only one node inside. Since symmetry properties, we consider a node is gravity of tetrahedron. We found the distance is more than we had. In mathematics, we figure out that the bubble salt form is minimum path and minimum energy structure. In 2010 American Journal of Physics, we want to find something to explain why the bubble salt form is not minimum path. We'll explore it later.
Now we are going to introduce the standard tree of hexahedron. First, we make a standard tree of square, then move it into the center of hexahedron. Then we consider these 4 rectangles. We find the standard tree of these rectangles and rotate them with an angle. And we found when the 4 rectangles are equal 15 degrees, the blue edge will match the pink edges. So there are 6 standard points in hexahedron, and this is the standard tree of hexahedron. And in bubble salt experiment, we found there are only 4 nodes in hexahedron. By calculus, we can find the minimal path, which is larger than the result we found in mathematics.
Next, we'll introduce the standard tree of octahedron. There are 8 faces, 6 vertices, and 12 edges in an octahedron. The 12 edges is happen to be the edge of three squares. Each square has 2 standard points, so we have 6 standard points now. These 6 points just be vertices of hexagon after calculation. By inner product, we know that each point connects the adjacent vertices of octahedron is 120 degrees, and this graph is exactly the bubble sort form of octahedron. But by former experience, it should be 2 points less than vertices of polyhedron. That is, there are 4 standard points of octahedron, so we won't remove 2 of them, and there is no cycle in the tree. So we remove the paths connected repeatedly, the vertices of octahedron, and remove the path which cause cycle. Finally, we remove the 2 points, which has symmetrical to the gravity of octahedron, and connect the tree. Now we have the standard tree of octahedron, which has 4 standard points and 9 edges. Then we make a mathematical model and find a shorter path than we had. Then we prove it in calculus. The simulation result match our proof. We show the proof on the test.
Now we are going to introduce the standard tree of octahedron. There are 12 faces and 20 vertices, and we have 2 methods. Method 1, we consider a hexahedron in dodecahedron, and there are 6 standard points in hexahedron. Then we divide dodecahedron to 6 same parts and the hexahedron, and we connect the red edges. So this is the standard tree of method 1. And method 2, we consider 3 golden rectangles. Each rectangle has 2 standard points, so there are 6 standard points, which form an octahedron. And octahedron has 4 standard points, so there are 10 standard points now. But by our former experience, the dodecahedron has 26 standard points, so it should have 18 standard points. So we choose the middle point of these red edges. So we have the standard tree of dodecahedron, and the path in method 2 is less than the path in method 1.
Next, we'll introduce the standard tree of octahedron. There are 20 faces, 12 vertices, and 30 edges in an octahedron. The 12 edges is happen to be the edge of 3 golden rectangles. Each rectangle has 2 standard points, so we have 6 standard points, which is vertices of octahedron. By former experience, there is 4 standard points in an octahedron, so we have 10 standard points in an octahedron. The red path is standard tree of octahedron. In the same way, we use algebra to make a simulation result, match our proof.
Result and discussion. We show our result on this table and compare with previous result. Tetrahedron and hexahedron are known, and we verify the result. And the previous result of octahedron and dodecahedron are errors, so we revise the result. Then we propose the standard tree of octahedron. Then in conclusion, we use mathematical software algebra to find the standard tree of Platonic polyhedron, and we finally prove it from convex n-gon to 3 dimensions. And we compare the bubbles of experiment. And in 2 dimensions, the number of vertices of a regular polygon is phi, and the number of standard points is x. Then we have a rule of s equal phi minus 2. And in 3 dimensions, the number of vertices of a Platonic polyhedron is phi, and the number of standard points is s. And suppose s equal phi minus 2 also holds, then we prove the minimum path we found. And in our future prospects, we know the structure of adenovirus is an octahedron, and standard tree has a minimal energy. So if we can destroy the structure, maybe we can kill the viruses. And there are many airports use the structure of polyhedron. And how can we spend less money and also have stable structure? maybe we can consider our research. And this is our reference. Thanks for listening.